For 4 billion years, longer than life has existed on Earth, an ocean has been moving in total darkness beneath the ice of a moon orbiting Jupiter. No sunlight, no surface, no witness. Heated from within by the gravitational squeeze of a giant planet, it has been dissolving rock, cycling chemistry, and pressing upward against a cracked ceiling of ice, depositing traces of itself on the surface again and again, with no one watching. Then, in 2022, a telescope less than a year old turned toward that surface for a few minutes and read the record. The James Webb Space Telescope detected carbon dioxide concentrated exactly where the ice has been, recently broken open, and the chemistry pointed straight down toward a hidden ocean that may hold twice the volume of every sea on Earth combined. Webb did not discover Europa. It caught up to it, and what it found makes this frozen moon far harder to ignore than it has ever been. If you enjoy deep explorations into the science, quietly rewriting what we know about our own solar system, consider hitting that like button and subscribing. It costs nothing, and it helps more people find work like this. Now, let's begin. In September 2023, 2 separate teams of scientists published their results on the same day in one of the most respected journals in the world. Both teams had used the same telescope, both had pointed it at the same target, and both reached the same unsettling conclusion. The James Webb Space Telescope had detected carbon dioxide on the surface of Europa, Jupiter's ice-covered moon, and the carbon dioxide was not where anyone would put it if it had arrived from space. It was concentrated in a specific region, a geologically young zone of disrupted and refrozen ice called Tara Regio, and its distribution, its chemical form, and its relationship to the terrain beneath it all pointed toward one source: the ocean below, not an ocean anyone has ever seen directly. Not an ocean confirmed by a submarine or a drill or a camera lowered through the crust. An ocean inferred from decades of gravitational data, magnetic field readings, surface geology, and now, for the first time, from chemical evidence that something carbon-bearing rose through kilometers of ice and left its mark on the frozen surface above. Webb did not find life on Europa. It did not detect a signal or a structure or a movement. What it found was arguably more consequential. It found that the chemistry of a hidden world is leaking upward through the ice, in a place where the crust has been recently broken and reassembled, and that leakage carries carbon, one of the 6 elements every known form of life requires to exist. This is what the title means. When we say Webb saw Europa for the first time, we do not mean humanity discovered Europa for the first time. Europa has been known since 1610, when Galileo Galilei turned a crude telescope toward Jupiter and noticed 4 points of light moving around the planet. Europa was one of them. It has appeared in textbooks and mission plans and science fiction for centuries. What, for the first time, means is something more specific and far more important. For the first time, a telescope with the spectral power of Webb examined Europa's surface chemistry at a resolution and sensitivity that no previous instrument could match. And what it revealed was not just confirmation of something scientists hoped might be true. It was a chemical fingerprint that tightens the connection between the icy surface we can see and the liquid ocean we cannot, in a way that makes the whole system feel less like a hypothesis and more like a place. To understand why this matters, you need to understand what Webb actually did. The James Webb Space Telescope orbits the Sun approximately 1.5 million kilometers from Earth, at a gravitational balance point called the second Lagrange point. From that position, Webb looks outward into the universe with instruments tuned primarily to infrared light, the wavelengths just beyond what human eyes can detect. Infrared is the language of heat, of molecular vibration, of chemistry at a distance. When infrared light hits a surface, different molecules absorb and reflect it at different wavelengths. Carbon dioxide absorbs infrared at a specific set of wavelengths. Water ice absorbs it at others. Sulfur compounds, salts, organic molecules, each leaves a distinct spectral signature, a chemical fingerprint written in light. This principle, called spectroscopy, is one of the most powerful tools in all of science, and it works because of a fundamental fact about how molecules interact with light. Every molecule vibrates. The atoms within it stretch, bend, and rotate relative to each other at frequencies determined by the molecule's structure, its mass, and the strength of the bonds holding it together. When a photon of infrared light arrives at a surface and its energy matches the vibrational frequency of a particular molecular bond, the molecule absorbs that photon. The light at that specific wavelength disappears from the reflected signal. A different molecule, with different bonds and different vibrational modes, absorbs at a different wavelength. The pattern of missing wavelengths in the reflected light tells you which molecules are present, without touching anything, without collecting a sample, without being anywhere near the surface you are studying. This is not a rough approximation. Molecular absorption features are precise. Carbon dioxide absorbs strongly at a wavelength near 4.2 to 5 micrometers due to the asymmetric stretching of its two carbon-oxygen bonds. Water ice has its own distinct absorption bands at different wavelengths: sulfur dioxide, methane, ammonia. Each molecule writes a different signature in the infrared spectrum, and those signatures do not overlap in ways that create confusion if your instrument is sensitive enough to separate them. Webb's near-infrared spectrograph is exactly that sensitive. It can split incoming light into thousands of individual wavelength channels, each one recording how much light arrived at that precise color. The result is not a photograph. It is a chemical inventory, pixel by pixel, of what molecules sit on the surface of a world more than 600 million kilometers away. The sheer improbability of this should not be lost. Europa, as seen from Webb's position near the second Lagrange point, is a tiny disk of reflected sunlight embedded in the glare of Jupiter. The infrared photons that carry its chemical information have already traveled from the Sun to Jupiter's orbit, bounced off Europa's ice, and then traveled all the way back to the inner solar system to reach Webb's mirror. By the time those photons arrive, they are extraordinarily faint. The signal from a specific molecular absorption band on a small region of Europa's surface is a whisper inside a roar of background light. Extracting that signal requires not only a large, cold, precisely shaped mirror, which Webb provides with its 6.5-meter gold-coated primary, but also an instrument capable of isolating that whisper by wavelength and spatial position simultaneously. The near-infrared spectrograph does this by passing the incoming light through a series of optical elements that sort it by wavelength before it reaches the detector, producing a spectrum for each spatial element on the target. The result is a data cube, 3 dimensions of information, 2 spatial and 1 spectral, from which researchers can extract a chemical map of the surface. The observations of Europa took only minutes of telescope time, but those few minutes produced a data cube that 2 independent research teams spent months analysing, and both teams converged on findings that changed how scientists think about this moon. The first team, led by Geronimo Villanueva at NASA's Goddard Space Flight Center, detected 4 distinct spectral features of carbon dioxide ice on Europa's surface. They found that the carbon dioxide was not evenly spread. It concentrated heavily in Tara Regio, a region dominated by chaos terrain, which is a term planetary scientists use to describe areas where the icy crust appears to have been broken apart, jumbled, and refrozen into rough, uneven blocks. Chaos terrain on Europa is not decorative. It is geological evidence that something disrupted the surface from below. The leading explanation is that warm water, or warm ice, from the interior rose upward, destabilized the crust, caused sections to fracture and tilt and drift, and then the surface refroze over the disrupted zone. Tara Regio is one of the largest and most prominent chaos regions on Europa, spanning roughly 1,800 kilometers across the moon's surface. The second team, led by Samantha Trumbo at Cornell University, reached a complementary conclusion. They mapped the carbon dioxide distribution and found it concentrated not just in Tara Regio, but also in portions of another chaos region called Pauis Regio. More importantly, they connected their finding to earlier Hubble Space Telescope observations that had detected ocean-derived sodium chloride, common salt, in the same region, salt from the ocean below, now carbon dioxide in the same disrupted terrain. The chemical evidence was stacking in a single direction. Material from the interior ocean is reaching the surface, and the places where it shows up are exactly the places where the ice has been most recently broken. This is the critical point that separates Webb's contribution from everything that came before. Scientists have suspected Europa has a subsurface ocean since the 1970s. The Voyager flybys in 1979 revealed a strangely smooth, ice-covered world, crisscrossed by fractures that looked like cracks in a frozen lake. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, measured Europa's magnetic field and found the signature of a conductive layer beneath the surface, almost certainly a global saltwater ocean. Galileo also captured images of chaos terrain, ridged plains, and features that strongly suggested geological activity driven by tidal interaction with Jupiter. The evidence for the ocean has been building for decades. But evidence that the ocean exists is different from evidence about what the ocean contains. Knowing there is water beneath the ice tells you something important. Knowing that carbon from that water is reaching the surface tells you something else entirely. Carbon is not just another element on the periodic table. It is the backbone of every biological molecule on Earth. Proteins, fats, sugars, DNA, every structure that makes life possible is built on a framework of carbon atoms bonded together. When astrobiologists evaluate whether an environment could support life, they look for a short list of requirements: liquid water, a source of chemical energy, and the right elements, particularly carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Europa was already known to have liquid water in staggering quantities. The tidal energy from Jupiter provides a heat source, but whether the ocean contained carbon in meaningful amounts was an open question. Webb answered part of that question. The carbon dioxide on Europa's surface appears to originate from an internal source. Both research teams reached this conclusion through different but converging lines of reasoning. If the carbon dioxide had been delivered by meteorite impacts, you would expect it to be distributed more evenly across the surface, or concentrated in older terrain where impacts have had more time to accumulate material. Instead, it is concentrated in geologically young chaos terrain, where the surface has been recently disrupted. Carbon dioxide is also unstable on Europa's surface. Jupiter's intense radiation environment breaks down carbon dioxide over time, meaning any carbon dioxide you see today must have been deposited relatively recently in geological terms. If it had been sitting on the surface for hundreds of millions of years, radiation would have destroyed it. Its presence in young terrain, combined with its instability, points strongly toward recent delivery from below. Villanueva's team also measured the carbon isotope ratio in the detected carbon dioxide. Carbon comes in two stable forms: carbon-12, which has 6 protons and 6 neutrons, and carbon-13, which has 6 protons and 7 neutrons. The ratio between these two isotopes can sometimes reveal how carbon-bearing molecules formed. The team measured a carbon-12 to carbon-13 ratio of approximately 83 plus or minus 19. This ratio is broadly consistent with what you might expect from carbon processed in an ocean environment, but the uncertainty is too large to draw firm conclusions about the specific chemical pathway. The isotope data is suggestive, not definitive. It adds a clue without closing the case. What the data does close, or very nearly closes, is the question of whether Europa's surface chemistry is connected to the ocean below. For years, scientists debated the degree to which Europa's ocean communicates with its surface. Some models suggested the ice shell is thick, rigid, and largely sealed, with the ocean trapped deep below and no mechanism for material exchange. Other models proposed that the ice is thinner in some regions, that warm plumes of water or slush occasionally punch through or approach the surface, and that chaos terrain represents the aftermath of such events. Webb's detection of ocean-derived carbon dioxide in chaos terrain supports the second picture. The surface and the ocean are not fully separated. There is a connection, and that connection is chemically meaningful. Think about what this means in practical terms. Europa looks from a distance like a smooth white billiard ball streaked with brown and tan lines. It appears clean, cold, inert, the kind of world you glance at in a textbook and move on from. But Webb's data says the surface is not a passive shell. It is a chemically active boundary layer that carries traces of the liquid world beneath it. The brown and tan discolorations that mark chaos terrain are not just visual features, They are chemical signatures. They are places where the ocean's composition has been translated, incompletely and imperfectly, onto the frozen exterior. Every time you look at a chaos region on Europa, you are looking at a window, not a wall. This reframing matters because it changes what Europa is in the scientific imagination. Before Webb, Europa was a famous candidate, an icy moon that probably has an ocean, that might have the right chemistry, that could potentially harbour conditions suitable for life. Those are all hedge statements. Probably, might, could, potentially. The language of possibility. After Webb, the hedging gets harder to maintain. The ocean is not just inferred from magnetic data and gravitational models. Its chemical content is showing up on the surface. Carbon from below is arriving in the places where the crust has been most recently cracked open. The gap between Europa might be interesting, and Europa's ocean is leaving chemical evidence on the ice. It is not a small gap. It is the difference between a suspicion and a physical measurement. None of this means Webb found life. That distinction is essential and must be stated clearly. Carbon dioxide on a surface is not a biosignature. It is a geochemical observation. Carbon is necessary for life as we know it, but carbon alone does not indicate biology. Volcanoes produce carbon dioxide. Chemical reactions between water and rock produce carbon dioxide. The carbon Webb detected could have formed through entirely non-biological processes in the ocean or at the ocean-rock interface. What the finding does is confirm that one of the essential ingredients for habitability, carbon availability, is present in Europa's ocean system and is being transported to the surface through geological processes. That is not a life detection. It is a habitability detection. And in the hierarchy of astrobiology, confirming habitability is the necessary step before you can even begin asking whether anything lives there. The specificity of the finding is what gives it weight. Webb did not detect a vague signal spread across an entire hemisphere. It detected a specific molecule, carbon dioxide, in a specific chemical form, mixed with other compounds, in a way that indicates a complex, rather than pure ice, concentrated in a specific geological setting, chaos terrain, that has independent evidence for recent surface-ocean exchange. Every layer of specificity narrows the range of possible explanations and makes the ocean origin interpretation stronger. This is not a case where scientists are reading meaning into ambiguous data. The data has structure. The structure points downward, through the ice, into the liquid below. There is another detail from the Webb observations that deserves attention, even though it is a negative result. Villanueva's team also searched for evidence of active plumes erupting from Europa's surface. The Hubble Space Telescope had reported tentative detections of water vapor plumes in 2013, 2016, and 2017, but those detections were never fully confirmed and remained controversial. If Europa has active plumes shooting water vapor into space, Webb's sensitivity should have been able to detect them. The team found no evidence of plumes during their observations. No water vapor, no carbon monoxide, no methanol, no ethane, no methane emissions above the surface. This non-detection does not mean plumes do not exist. It means they were not active during the specific window when Webb observed Europa. Plumes, if they occur, may be transient, erupting unpredictably and shutting off before the next observation. The team set strict upper limits on how much material could be escaping the surface, which will help constrain future models of Europa's geological activity. But the absence of plumes during this observation actually makes the carbon dioxide finding more striking. The carbon dioxide on the surface was not delivered by an active eruption caught in the act. It was already there, embedded in the ice, concentrated in disrupted terrain, evidence of a process that happened before Webb looked. The ocean did not need to be erupting for its chemistry to be visible. The ice itself carried the record. This is what makes Webb's observation of Europa genuinely new. Previous telescopes could see Europa. They could photograph its surface, measure its size, map its largest features. The Galileo spacecraft could fly close and study its magnetic field, its gravity, its surface geology in detail. Hubble could detect hints of sodium chloride and tentative plume activity, but none of these instruments could read the surface chemistry with the precision and sensitivity that Webb's near-infrared spectrograph provides. Webb did not just see Europa, it tasted the ice. It identified what molecules are present, where they concentrate, and how they relate to the geological structures beneath them. That capability is what turns Europa from a dot with a backstory into a world whose hidden chemistry is beginning to surface in measurable, mappable, interpretable ways. And the initial results from 2023 were only the beginning. By 2025, a follow-up study by Richard Cartwright and colleagues used Webb data to examine Europa's chaos terrain in even greater detail. They found additional evidence for carbon-13, the heavier carbon isotope, concentrated in Tara Regio, and every analytical pathway they tested pointed back toward an internal origin. The roads, as the researchers put it, all led back to the ocean. Then, in early 2026, a team led by Gideon Yoffe applied a technique called spectral decomposition to Webb's observations of Europa's leading hemisphere. They discovered that carbon dioxide is not confined to Tara Regio alone. It extends across multiple chaos terrains and correlates with regions where the ice texture is anomalous, meaning the ice itself has been physically altered in ways consistent with disruption and refreezing. The chemical map is getting richer, the pattern is getting clearer, and the pattern keeps saying the same thing. The surface and the ocean are talking to each other, and Webb is learning to listen. What lies beneath that surface? What kind of ocean produces this chemistry? And why the sheer physical scale of it should unsettle anyone paying attention is where this story goes next. Europa is smaller than Earth's moon. Its diameter measures approximately 3,122 kilometers, which makes it the smallest of Jupiter's 4 large Galilean moons, and only slightly smaller than our own moon in sheer physical width. From a distance, it looks like a pale marble scratched with faint reddish-brown lines, the kind of object you might mistake for geologically dead. Frozen solid from crust to core, a relic of the early solar system preserved in ice. That appearance is a lie. Beneath the smooth, reflective surface of Europa sits what may be the largest ocean in the entire solar system relative to the body that contains it, and certainly one of the most scientifically consequential bodies of liquid water ever identified anywhere beyond Earth. Scientists estimate that Europa's subsurface ocean holds roughly twice the volume of all of Earth's oceans combined. Think about that number for a moment. Every ocean on Earth, the Pacific, the Atlantic, the Indian, the Arctic, the Southern, every bay, every trench, every cubic meter of salt water on this planet, doubled, contained inside a moon that could fit inside the continental United States. The ocean is global, meaning it wraps entirely around the moon beneath the ice, a continuous shell of liquid water with no continents, no coastlines, no exposed surface. It exists in permanent darkness, sealed beneath a crust of ice estimated to be tens of kilometers thick, pressing down on water that may extend 60 to 100 kilometers deep before reaching a rocky seafloor below. The total thickness of the water layer, counting both ice and liquid, is approximately 100 to 170 kilometers depending on the model. But the liquid portion alone dwarfs anything on Earth. Europa's interior is layered, like Earth, but with a structure that reflects its unique composition and history. At the center sits a metallic core, likely iron or iron sulfide, estimated to be roughly 600 to 700 kilometers in radius. Surrounding the core is a rocky silicate mantle, the bulk of the moon's mass, extending outward to where the water layer begins. This mantle is not passive. It is the source of whatever geological heat Europa generates internally, the interface where rock meets water, and possibly the site of hydrothermal processes that could have profound implications for chemistry in the ocean above. Above the mantle lies the water layer itself, the combined ice shell and liquid ocean that together account for the outermost 100 to 170 kilometers of the moon. The proportions are remarkable. On Earth, the ocean averages about 3.7 kilometers deep and covers 71% of the surface. Europa's water layer is roughly 40 times deeper than Earth's average ocean depth and wraps the entire body without interruption. The moon is, in a sense, more ocean than rock when measured by the fraction of its radius that water occupies. The existence of this ocean was not always obvious. Before 1979, Europa was little more than a point of light, a dot whose basic properties, size, approximate density, orbital period, were known but whose surface had never been resolved by any telescope on Earth or in space. The best ground-based images showed a fuzzy smear next to Jupiter's glare. Scientists expected that when a spacecraft finally flew close enough to photograph Europa, it would look much like Callisto, Jupiter's outermost large moon, a battered, cratered sphere pockmarked by 4 billion years of impacts. Callisto was the default assumption for what an icy moon should look like. Dead, dark, ancient. Every surface feature preserved from the early solar system like scars in stone. Voyager 1 arrived at Jupiter in March 1979 and returned the first resolved images of Europa. The pictures were low resolution, taken from a considerable distance, but they were enough to show something unexpected. The surface was bright, unusually bright, and smooth. There were hints of long, curved lines crossing the disk, but at the resolution available, it was difficult to tell whether they were ridges, fractures, or imaging artifacts. The scientific team, led by Imaging Team Chief Brad Smith, noted that Europa looked strangely featureless compared to the heavily cratered surfaces of Ganymede and Callisto. But the data were limited, and Europa was not the primary target of the Voyager 1 encounter. Jupiter itself and the volcanic fury of Io commanded most of the attention. 4 months later, in July 1979, Voyager 2 passed through the Jupiter system on a different trajectory that brought it closer to Europa. The higher resolution images that came back changed everything. Europa's surface was not just smooth, it was the smoothest solid surface in the entire solar system. There were almost no impact craters. The globe was covered in water ice, brilliantly white in some areas, faintly discoloured in others, and crisscrossed by an extraordinary network of lines. These were not subtle markings. They were vast, continent-spanning features, some stretching thousands of kilometres across the surface, thin and sharp and interlocking in patterns that had no precedent in planetary science. Some were double ridges, paired lines running in parallel with a shallow trough between them. Others were broad, diffuse bands, where the surface appeared to have been pulled apart and filled in with fresh material from below. The overall impression was unmistakable. Europa looked like a frozen lake, whose surface had cracked, shifted, and refrozen, over and over, erasing old features and replacing them with new ones. The scarcity of craters was the most telling detail. On most airless, geologically dead worlds, craters accumulate over billions of years because there is no process to erase them. The nearly crater-free surface of Europa meant the ice was young in geological terms, perhaps only 60 to 90 million years old across most of the visible terrain. Something was continuously resurfacing the moon, smoothing over old impacts and replacing them with fresh ice. The implication was immediate and startling. Europa was not a dead world. It was geologically active, and the most natural explanation for that activity, given the moon's icy composition and its position deep within Jupiter's gravitational influence, was liquid water beneath the surface. An ocean, hidden, unseen, but leaving its signature in the form of a surface that refused to hold on to the scars of time. The Voyager images electrified the planetary science community. In the span of a few months, Europa went from an unremarkable dot to one of the most intriguing objects in the solar system. But the Voyager data had limits. The cameras were designed for broad survey imaging, not for detailed compositional or geological analysis. The flybys were brief and the spacecraft carried no magnetometer sensitive enough to probe Europa's interior. The ocean hypothesis was compelling but circumstantial, supported by the surface appearance and by theoretical models of tidal heating, but not by any direct measurement of what lay beneath the ice. That measurement would have to wait 16 years. The Galileo spacecraft provided the evidence that turned suspicion into near certainty. Between 1995 and 2003, Galileo orbited Jupiter and made multiple close flybys of Europa, measuring its gravity, imaging its surface in detail, and, most critically, studying its magnetic field. The magnetometer story deserves particular attention because it remains one of the most elegant planetary discoveries of the past half-century. Jupiter has the most powerful magnetic field of any planet in the solar system, roughly 20,000 times stronger than Earth's. This field rotates with Jupiter, which spins once every 10 hours, sweeping its magnetic influence past the orbits of its moons like a cosmic lighthouse beam. Any electrically conductive material within range of this rotating field will respond. Free-moving charged particles, like ions dissolved in salt water, will shift in response to the changing magnetic environment, generating their own secondary magnetic field. This secondary field, called an induced field, acts as a telltale signature. If you can detect it, you can infer the presence of a conductive layer, even if you cannot see it directly. The principal investigator for Galileo's magnetometer experiment, Margaret Keevelson, and her team measured the magnetic environment around Europa during multiple flybys and found exactly this signature. Europa was producing an induced magnetic field that varied in strength and orientation as Jupiter's field rotated past the Moon. The pattern was consistent with a global layer of electrically conductive material beneath the surface. Rock is not conductive enough to explain the signal. Ice is an insulator. The most natural and physically consistent explanation was a global ocean of salt water, a brine with enough dissolved ions to carry electrical currents strong enough to generate the observed field. The data did not prove liquid water beyond all mathematical doubt, but it made every alternative explanation far less convincing. Kivelson's results, published across several papers in the late 1990s and early 2000s, became the single strongest piece of evidence for Europa's ocean and remains so today. The question that follows immediately is simple and profound. How does a moon this small, this far from the Sun, keep a liquid ocean from freezing solid? Europa orbits Jupiter at a distance of approximately 671,000 kilometers, and Jupiter itself orbits the Sun at roughly 778 million kilometers. At that distance, solar energy is weak. Europa's surface temperature hovers around -160 degrees Celsius. Under normal circumstances, a body this cold should be frozen through. Any primordial heat left over from its formation should have radiated away billions of years ago. The ocean should not exist. The answer is Jupiter. Specifically, the answer is gravity, and what gravity does to Europa's interior every time the Moon completes an orbit. Europa does not orbit Jupiter in a perfect circle. Its orbit is slightly elliptical, and that eccentricity is maintained by a gravitational relationship with two neighbouring moons, Io and Ganymede. The three moons are locked in what physicists call a Laplace resonance. For every orbit Ganymede completes around Jupiter, Europa completes exactly 2, and Io completes exactly 4. This resonance prevents Europa's orbit from circularizing over time, which it would naturally tend to do through tidal dissipation. Instead, the orbit stays slightly elongated, and that elongation is the key to everything. As Europa moves along its elliptical path, its distance from Jupiter changes. When it swings closer, Jupiter's gravitational pull is stronger. When it moves farther away, the pull weakens. This rhythmic variation in gravitational force does something remarkable to Europa's interior. It flexes the Moon. The entire body of Europa stretches and compresses slightly with each orbit, like a rubber ball being squeezed and released over and over. This flexing generates friction inside the Moon, and friction generates heat. The process is called tidal heating, and it is the engine that keeps Europa's ocean liquid. The amount of heat generated by tidal flexing is not trivial. Estimates vary depending on the model, but most calculations place Europa's tidal heat production somewhere in the range of 1/10 to 1 terawatt globally. For comparison, the total heat flowing out of Earth's interior is approximately 47 terawatts, driven primarily by radioactive decay in the mantle and residual heat from formation. Europa is much smaller, but tidal heating provides a concentrated and continuous energy source that does not depend on radioactive elements or leftover formation heat. As long as the orbital resonance with Io and Ganymede persists, and it has persisted for billions of years, the tidal engine keeps running. The ocean stays liquid. The ice above it remains dynamic. The ice shell itself is one of the most studied and debated features in planetary science. How thick is it? This question matters enormously because the thickness of the ice determines how easily material can move between the surface and the ocean. A thin shell, perhaps 5 to 10 kilometers thick, would allow more direct exchange. Cracks could potentially penetrate all the way through. Warm plumes of water might occasionally breach the surface. A thick shell, 20 to 40 kilometers deep, would make exchange more difficult but not impossible, requiring convection within the ice itself to transport material upward over geological timescales. For decades, estimates ranged widely. Some models based on the morphology of impact craters suggested the ice might be as thin as 3 to 4 kilometers in some areas. Other models based on thermal equilibrium calculations predicted thicknesses of 20 to 30 kilometers or more. The debate was difficult to resolve because no instrument had directly measured the shell's depth. Then, in 2022, NASA's Juno spacecraft, which primarily studies Jupiter itself, made a close flyby of Europa and turned its microwave radiometer toward the Moon's surface. Microwave radiation penetrates ice to varying depths depending on the ice's temperature, composition, and structure. By analysing how microwaves emitted from Europa's interior passed through the ice shell, the Juno team was able to estimate its thickness. Their result, published in late 2025 in the journal Nature Astronomy, placed the ice shell at approximately 29 kilometers thick, plus or minus 10 kilometers. For the idealized case of pure water ice, that figure is consistent with a thermally conductive shell overlying a liquid ocean, but the data also revealed something else. The ice is not pristine. Fractures, pores, or other scattering features extend to depths of hundreds of meters below the surface. The shell is cracked. Not clean, not sealed, not a uniform barrier. It is fractured ice sitting on top of an ocean, and those fractures reach deep. The nature of those subsurface features matters more than a simple statement about cracking can convey. The Juno microwave radiometer does not image fractures the way a camera photographs a crack in a wall. It detects scattering, the disruption of microwave signals as they pass through material that is not uniform. Something within the upper hundreds of meters of the ice shell is breaking up the microwave signal in ways that smooth, pure ice would not. The most likely explanations involve physical heterogeneity within the shell itself. Microfractures, hairline cracks too small to see from orbit, but numerous enough to affect how radiation propagates through the ice. Pockets of brine, small volumes of trapped liquid where salty water has not fully frozen, held in a slushy or liquid state by the freezing point depression that dissolved salts provide. Voids and porosity created by thermal stress as the shell flexes with each tidal cycle, expanding and contracting in response to Jupiter's gravitational pull, gradually working tiny gaps into the crystalline structure of the ice. None of these features would be visible from the surface. They exist inside the shell, hidden beneath the smooth exterior, detectable only because they alter the way microwaves travel through the material. But their presence changes what the ice shell is, physically and conceptually. A shell with internal fractures, brine inclusions, and porosity is not a monolithic slab of frozen water. It is a mechanically complex layer with internal texture, a medium through which dissolved chemicals and trapped fluids can migrate along pathways that do not require a crack to reach all the way from the ocean to the surface. Brine pockets could serve as intermediate reservoirs, collecting ocean-derived material that percolates upward through the warmer, softer ice near the shell's base, and holding it at shallower depths where further geological processes, fracturing, convection, chaos terrain formation, can bring it the rest of the way to the exterior. The shell is not a wall with occasional holes in it. It is a porous, heterogeneous, mechanically active layer with internal structure that extends far deeper than surface features alone would suggest. This finding matters because it connects directly to what Webb observed on the surface. If the ice shell were a perfect unbroken layer of solid water ice tens of kilometers thick, you would not expect ocean-derived material to show up on the exterior. The shell would be too thick and too rigid to allow chemical exchange on any reasonable timescale. But if the shell is fractured, if warm ice convects slowly upward through the interior, if sections of the crust periodically break apart and refreeze in the chaos terrain that Webb mapped, and if the upper hundreds of meters are riddled with microfractures and brine inclusions that provide additional pathways for chemical migration, then the barrier between ocean and surface becomes permeable. Not perfectly permeable, not a free-flowing channel, but permeable enough that over thousands or millions of years, molecules from the ocean can work their way upward and leave their mark on the ice above. Chaos terrain is the physical evidence that this permeability is real. When you look at Europa's surface in detail, the chaos regions stand out as patches where the normal pattern of ridges and smooth plains has been disrupted. Blocks of ice appear to have broken free, rotated, tilted, and refrozen in new positions, like ice flows on a thawing river. The texture is rough, jumbled, disordered. Planetary scientists have proposed several mechanisms for forming chaos terrain, but the leading explanation involves the upwelling of warm material from below. In this model, heat from the ocean or from a warm pocket of water within the ice shell rises toward the surface. The overlying ice thins, weakens, and eventually collapses or fractures. Liquid or warm slush contacts the cold surface ice, causing melting and refreezing. The blocks of ice shift position during the disruption and then become locked in place as the surface refreezes. Tara Regio, the region where Webb detected the highest concentration of carbon dioxide, is one of the most extensive chaos regions on Europa. It spans approximately 1,800 kilometers and is located on the Moon's leading hemisphere, the side that faces forward as Europa orbits Jupiter. Previous observations by the Galileo spacecraft imaged Tara Regio's rugged terrain, though only a handful of high-resolution images were returned due to technical limitations with Galileo's antenna system. The spacecraft's high-gain antenna, a large umbrella-shaped dish designed to relay data at high speeds, failed to deploy properly early in the mission. Engineers were forced to rely on a much smaller low-gain antenna that transmitted data thousands of times more slowly. This meant that Galileo could only return a fraction of the images and measurements it collected during each flyby. Despite this crippling limitation, the images that did arrive revealed Tara Regio as a place where the surface had been dramatically reworked, and the highest resolution frames from the 15th and 17th Europa flybys in 1998 showed details as fine as 220 meters per pixel, enough to confirm the chaotic, disrupted character of the terrain. What makes Tara Regio especially significant is that it is not just geologically young, it is chemically distinct. Before Webb, the Hubble Space Telescope detected evidence of sodium chloride concentrated in Tara Regio. Sodium chloride is ordinary table salt. On Earth, it dissolves readily in ocean water. Finding it on Europa's surface, concentrated in a region of disrupted ice, strongly suggested that salty ocean water had reached the surface and evaporated or sublimated, leaving its dissolved salts behind. Webb's carbon dioxide detection added a second chemical data point to the same location. First salt, now carbon, both sourced from below, both concentrated in terrain that shows clear evidence of surface-ocean exchange. The accumulation of chemical evidence in Tara Regio transforms it from an interesting geological feature into something closer to a reading station, a place on the surface where you can begin to deduce what the ocean below contains without ever breaking through the ice. This is an extraordinary concept. We cannot send a submarine to Europa's ocean. We cannot drill through 29 kilometers of ice, at least not with any technology that currently exists or is planned. But the ocean itself may be delivering samples to the surface through geological processes that have been operating for millions of years. Those samples are degraded, incomplete, and transformed by radiation and surface conditions. But they are there, and Webb can read them. The connection between surface chemistry and ocean chemistry is not perfectly straightforward. Europa's surface is bombarded by intense radiation from Jupiter's magnetosphere. That same powerful magnetic field whose induced signature revealed the ocean also traps charged particles, protons, electrons, and heavy ions in radiation belts that sweep across Europa's orbits. This radiation slams into Europa's icy surface and drives chemical reactions. It breaks apart water molecules, producing hydrogen, oxygen, and hydrogen peroxide. It can alter carbon dioxide, sulfur compounds, and organic molecules, rearranging their chemistry in ways that obscure the original composition. Any material that reaches the surface from the ocean does not stay pristine for long. It gets irradiated, processed, and chemically modified. This radiation processing is both a complication and an opportunity. It is a complication because it means the carbon dioxide Webb detected may not be in the exact chemical form it was in when it left the ocean. The molecule might have been delivered as a different carbon-bearing compound, perhaps dissolved carbon dioxide, perhaps carbonate minerals, perhaps organic molecules, and then transformed into carbon dioxide on the surface through radiation chemistry. both research teams acknowledged this possibility, they could not definitively determine the original form of the carbon. What they could determine was that the carbon itself, the element, originated from inside Europa, not from external delivery. The radiation processing is also an opportunity because it creates oxidants on the surface, molecules like oxygen and hydrogen peroxide that are chemically reactive and could serve as energy sources for biology. On Earth, many microorganisms survive by exploiting chemical energy rather than sunlight. Deep-sea hydrothermal vent communities, for example, thrive in total darkness by using the chemical imbalance between hot, mineral-rich water rising from Earth's interior and the cold, oxygen-rich ocean above. If similar processes operate on Europa, the oxidants produced by radiation on the surface could be a critical ingredient. But only if they reach the ocean, only if there is a pathway for surface material to be transported downward through the ice shell, completing the chemical cycle. Surface material going down, ocean material coming up. A two-way exchange that connects radiation-driven surface chemistry with the liquid water environment below. The evidence that such a two-way exchange exists is exactly what has been building over the past several years. Hubble found salt going up. Webb found carbon going up. Juno found fractures going down. The Galileo magnetometer found a conductive ocean underneath all of it. No single measurement proves the complete cycle, but the converging lines of evidence are becoming difficult to explain without it. Now consider the environment at the bottom of that ocean. Europa's water layer sits atop a rocky silicate mantle. The boundary between ocean and rock is a seafloor, and that seafloor may be one of the most important geological boundaries in the solar system. On Earth, the interaction between ocean water and hot rock at mid-ocean ridges produces hydrothermal vents, fissures in the seafloor where superheated, mineral-laden water erupts into the cold ocean above. These vents create chemical gradients, energy sources that sustain entire ecosystems independent of sunlight. Tube worms, blind shrimp, heat-loving bacteria, complex communities of life that exist solely on chemical energy drawn from the interaction of water and rock. A study published in 2021 proposed that Europa's seafloor should be hot enough for active volcanism, driven by tidal heating in the Moon's silicate interior. If hydrothermal vents exist on Europa's seafloor, they would provide exactly the kind of chemical energy source that supports life on Earth's deep ocean floor. Hot water percolating through rock dissolves minerals and produces reduced chemical compounds like hydrogen sulfide and molecular hydrogen. When these reduced compounds meet the oxidants present in the ocean water, the resulting chemical reactions release energy that microorganisms can harvest. This is not speculative biology. It is observed chemistry. On Earth, this process has been sustaining life for billions of years in environments completely cut off from sunlight. Whether Europa's seafloor is actually volcanically active remains unconfirmed. Some models suggest the silicate interior generates enough tidal heat for active volcanism. Others propose a weaker, more passive interaction where water simply percolates through porous rock without dramatic eruptions. The answer matters for habitability assessments, because active volcanism would provide a more concentrated energy source, while passive water-rock interaction would provide a more diffuse one. Both scenarios are consistent with the chemical evidence Webb detected on the surface. Both would produce carbon-bearing compounds in the ocean, and both would create conditions that, on Earth, are associated with life. The depth of Europa's ocean adds another dimension to the picture. If the liquid layer extends 60 to 100 kilometers beneath the ice, the water pressure at the seafloor would be considerable. Europa's gravity is only about 1/7 of Earth's, which reduces the pressure that each kilometer of water generates. But the sheer depth compensates. On Earth, the Mariana Trench reaches approximately 11 kilometers, where the pressure is about 1,100 times atmospheric pressure at sea level. Europa's seafloor, depending on the model, would experience pressures roughly 1.5 to 2 times higher than that, because the ocean column is many times deeper, even though each meter of water contributes less pressure than it would on Earth. The combined weight of tens of kilometers of ice overhead and 60 to 100 kilometers of liquid water below it still produces a crushing environment by any terrestrial standard. Life on Earth exists at the pressures found in the Mariana Trench. Microorganisms thrive in those conditions. Whether life could exist at the even higher pressures of Europa's deep ocean is an open question, but nothing in known physics or biology suggests an absolute barrier at those levels. The temperature profile of the ocean is also important. The base of the ice shell sits at approximately -3 degrees Celsius, the freezing point of the salty brine that keeps the water liquid at that depth. Water temperature likely increases with depth due to heating from the seafloor below. The warmest water would be near the rocky bottom, where tidal heating warms the silicate mantle and drives whatever geological activity the seafloor supports. This temperature gradient would drive convection, with warm water rising from the bottom and cold water sinking from the top, creating circulation patterns that distribute heat, chemicals, and nutrients throughout the ocean. This convection is not a minor detail. In an ocean 60 to 100 kilometers deep, the temperature difference between the cold ice ceiling and the warm rocky floor could sustain vigorous overturning currents. On Earth, ocean circulation is driven by differences in temperature and salinity, a process called thermohaline circulation. The Gulf Stream, the deep water formation around Antarctica, the vast conveyor belt that moves water through every ocean basin on the planet, all of these currents arise because water at different temperatures and salt concentrations has different densities, and denser water sinks while lighter water rises. Europa's ocean would experience a version of the same physics. Cold, dense brine at the top sinking toward the seafloor, warm, less dense water at the bottom rising toward the ice. The resulting circulation would not just distribute heat, it would transport dissolved chemicals, ions, and particles throughout the entire liquid volume, mixing material from the seafloor upward toward the ice and cycling surface-derived material downward toward the rock. A deep ocean in convective motion is not a stagnant reservoir. It is a mixing engine, redistributing whatever the seafloor produces and whatever percolates down from the ice above. This circulation has direct implications for habitability. On Earth, ocean currents carry nutrients from the deep to the surface, sustaining the plankton that form the base of the marine food web. On Europa, currents would carry chemical energy from the seafloor upward, potentially distributing it throughout the ocean rather than confining it to a thin layer near the rock. If oxidants from the surface reach the upper ocean through ice fractures and tidal pumping, convection could draw them downward and mix them with reductants rising from below. The entire ocean would become a reaction vessel, a place where chemical gradients exist not just at the boundaries but throughout the liquid volume. Europa's ocean is not a stagnant pool. It is a dynamic, circulating fluid system that has been operating for potentially billions of years. The age of the ocean matters because life on Earth took hundreds of millions of years to emerge after the planet formed, and billions of years to develop complexity. If Europa's ocean is young, there may not have been enough time for meaningful chemistry to develop, let alone biology. But all evidence suggests the ocean is ancient. The Laplace resonance that drives tidal heating has been stable for most of the solar system's history. Models indicate Europa's ocean could have existed for over 4 billion years, roughly as long as Earth's own oceans. 4 billion years of liquid water. 4 billion years of water-rock interaction. 4 billion years of chemical evolution in an environment that, on paper, contains the ingredients for habitability. This is the context that makes Webb's carbon dioxide detection so consequential. The finding does not stand alone. It plugs into a larger picture that has been assembling for decades. An ocean with twice the volume of Earth's oceans. A heat source that has operated for billions of years. A rocky seafloor where water and rock may interact chemically. Fractures in the ice that allow material exchange between the surface and the deep. Convective circulation that mixes the ocean from top to bottom. And now, confirmed chemical evidence that carbon from the ocean is reaching the surface in the places where the ice has been most recently broken. Europa does not look threatening. It looks like a pale, clean sphere of ice hanging in the blackness near Jupiter. But the more data we gather, the more that clean appearance starts to feel like a mask. Beneath the smooth exterior lies a system of staggering physical scale and chemical complexity. An ocean in permanent darkness, heated from below, pressurized by kilometers of ice, circulating for eons, and now, through the cracks in the ice above, beginning to reveal its contents to anyone with a telescope sensitive enough to read them. What those contents actually mean for the question of habitability, what the chemistry tells us and what it cannot yet confirm, And why the word disturbing refers not to horror but to the uncomfortable weight of accumulating evidence is where this story goes next. There is a word in the title of this story that needs to be earned. Disturbing. Not shocking. Not terrifying. Not the kind of word you use when something jumps out of the dark. Disturbing in the scientific sense means something that unsettles a settled picture. Something that forces a revision. Something that was easier to live with before you had the data, and harder to live with after. What Webb found on Europa is disturbing because it takes a moon that scientists have discussed as a theoretical candidate for decades and moves it, measurably and chemically, closer to being a world where the ingredients for life are not just possible but physically present, connected and active. And once you see that, you cannot unsee it. To understand why the chemistry matters this much, you have to understand what scientists mean when they talk about habitability. Habitability does not mean a place is inhabited. It does not mean life exists there. It means the conditions necessary for life, as we understand them, are met. On Earth, every environment where life has been found shares three features: liquid water, a source of usable chemical energy, and the right elements in accessible forms, particularly the six that biochemistry depends on most heavily: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are sometimes abbreviated with the acronym CHNOPS, and they are the elemental foundation of every protein, every strand of DNA, every lipid membrane, and every metabolic reaction in every living organism ever studied on this planet. Europa has been evaluated against this checklist for years. Liquid water was effectively confirmed by the Galileo magnetometer data in the late 1990s. Chemical energy became plausible when scientists recognized that Jupiter's radiation creates oxidants on the surface that could, if transported into the ocean, react with reduced compounds from the seafloor to release energy. The CH-NOPS elements were the remaining question. Hydrogen and oxygen are abundant in water ice. Sulfur compounds have been detected on the surface, likely delivered both from volcanic Io and from internal processes. Nitrogen remains unconfirmed but is expected to be present in trace amounts based on solar system chemistry. Phosphorus has not been directly detected, but models of water-rock interaction suggest it should leach from silicate minerals on the seafloor over geological timescales. Carbon was the critical gap, not because scientists doubted it was there. Carbon is the fourth most abundant element in the universe. It would be surprising if Europa's ocean contained none. But science does not run on expectation. It runs on measurement, and until Webb, no instrument had the capability to identify carbon-bearing molecules on Europa's surface with enough spatial resolution to determine where they came from. Previous detections of carbon dioxide on Europa existed, stretching back to observations from ground-based telescopes and the Galileo spacecraft's near-infrared mapping spectrometer. But those earlier measurements lacked the sensitivity and spatial coverage to distinguish between carbon dioxide delivered by meteorites, produced on the surface by radiation processing of external material, or sourced from the interior ocean. The origin was ambiguous. The data could not settle the question. Webb settled it, or came as close to settling it as remote observation currently allows. The concentration of carbon dioxide in Tara Regio, a region with independent evidence for recent surface-ocean exchange, combined with the instability of carbon dioxide under Europa's radiation environment, combined with the chemical form of the detected molecules, which appeared to be mixed with other compounds rather than existing as pure ice, all pointed toward an internal source. Two independent teams reached this conclusion through separate analyses of the same dataset. The convergence of two research groups on the same answer, using different analytical approaches and publishing simultaneously in the same journal, is the kind of scientific agreement that carries real weight. It is not proof in the absolute mathematical sense, but it is strong enough that the burden of evidence has shifted. Anyone arguing that the carbon dioxide on Tara Regio comes entirely from external sources now has to explain why it concentrates in chaos terrain, why it avoids older surfaces, and why its chemical form matches what you would expect from material processed through an ice shell rather than deposited from above. But confirming that carbon reaches the surface raises a question the Webb data alone cannot answer. How does carbon get into the ocean in the first place? The ocean did not form with a preloaded supply of carbon dioxide dissolved in it. waiting for geological processes to push it upward. The carbon had to come from somewhere, and understanding where closes the explanatory loop between the Webb detection and the deeper chemistry of Europa's interior. The most likely source is the rocky seafloor itself. Europa's silicate mantle is composed of minerals that formed when the Moon assembled from the same primordial material that built the rest of the solar system. That material contained carbon, locked in mineral structures and in organic compounds delivered by the same comets and asteroids that contributed to Europa's bulk composition. When ocean water comes into contact with this rock, especially at elevated temperatures near hydrothermal systems, chemical reactions begin dissolving minerals and releasing their constituent elements into the water. Carbon trapped in the rock can be liberated through several pathways. One pathway involves the thermal decomposition of carbonate minerals. Carbonates, compounds containing carbon and oxygen bonded in a specific crystal structure, are common products of water-rock interaction. When the seafloor temperature is high enough, these carbonates can break down, releasing carbon dioxide directly into the water. Another pathway involves reactions between water and silicate minerals rich in iron and magnesium, such as olivine and pyroxene. These minerals are expected to be abundant in Europa's mantle, based on the Moon's bulk density and formation history. When water interacts with these minerals at temperatures above roughly 200 degrees Celsius, a cascade of chemical reactions occurs. The iron in the minerals oxidizes, the water is chemically reduced, and molecular hydrogen is released as a byproduct. This process, called serpentinization, is one of the most important geochemical reactions on Earth's ocean floor, and it produces conditions that favor the formation of simple carbon-bearing molecules, including methane, formic acid, and carbon dioxide, from dissolved inorganic carbon. A third pathway involves Fischer-Tropsch type synthesis, a set of reactions in which carbon monoxide or carbon dioxide reacts with the molecular hydrogen produced by serpentinization to form more complex organic molecules. On Earth, these reactions have been documented at hydrothermal vents, producing a range of carbon compounds without any biological involvement. None of these reactions requires life. They require only rock, water, heat, and time. Europa has all four. The seafloor has been bathed in ocean water for potentially 4 billion years, with tidal heating maintaining temperatures that could drive these reactions continuously. Carbon released from the rock would dissolve into the ocean as dissolved carbon dioxide, carbonate ions, or bicarbonate, depending on the water's temperature and acidity. Over billions of years, even slow release rates would build up a significant reservoir of dissolved carbon in the ocean. That reservoir is what Webb detected the surface expression of. Carbon that was once locked in rock, liberated by water rock chemistry on the seafloor, dissolved into the ocean, carried upward by convection, delivered to the base of the ice shell, transported through the ice by geological processes, and deposited on the surface in chaos terrain where the crust had been recently broken. The chain is long, but every link in it is supported by known physics and chemistry. The carbon isotope data adds texture to this picture, even though it cannot yet deliver a definitive answer. Carbon-12 and carbon-13 are both stable isotopes, meaning they do not decay radioactively. They exist in a natural ratio throughout the solar system, roughly 89 carbon-12 atoms for every 1 carbon-13 atom. But different chemical and biological processes favor one isotope over the other, subtly shifting the ratio. On Earth, biological processes tend to prefer carbon-12 because it is lighter and reacts slightly more readily in enzymatic reactions. A strong depletion of carbon-13 in a sample can sometimes indicate biological processing, though abiotic processes can also produce isotopic shifts under certain conditions. Villanueva's team measured the carbon-12 to carbon-13 ratio on Europa at approximately 83 plus or minus 19. That range is wide enough to overlap with several possible formation scenarios, both biological and non-biological. It does not confirm life. It does not rule it out. What it does is provide a baseline measurement that future missions can refine with better instruments at closer range. If Europa Clipper, or a future lander, measures the isotope ratio with greater precision and finds a strong deviation from the expected solar system value, that deviation would become one of the most scrutinized numbers in the history of science. For now, the ratio is a placeholder, a first measurement where none existed before, waiting for sharper data to fill in what it means. The 2025 study by Richard Cartwright and colleagues pushed the isotope story further. Using Webb data focused on Europa's chaos terrain, the team detected carbon-13 signatures in Tara Regio specifically, and examined every plausible formation pathway. External delivery from meteorites could not easily explain the isotopic distribution. Surface production through radiation processing of externally delivered organics was possible, but required assumptions that did not match the observed spatial pattern. The most consistent explanation, as the researchers noted, was an internal origin. Every road led back to the ocean. That phrase, used by the researchers themselves, captures the state of the evidence. Not every road leads to life, but every road leads inward, downward, through the ice, into the liquid below. Then came the 2026 study by Gideon Yoffe and colleagues, posted to the archive preprint server and subsequently covered in the scientific press. This team applied a technique called spectral decomposition to Webb's observations of Europa's leading hemisphere. Rather than looking at the surface as a single average spectrum, they broke the signal into separate spectral components, each corresponding to a different chemical species or mixture. By analysing 9 separate spectral bands covering water ice, carbon dioxide, and other compounds, they were able to reconstruct the chemical layering of the surface with unprecedented detail. Their most significant finding was that carbon dioxide on Europa is not confined to Tara Regio. It extends across multiple chaos terrains on the leading hemisphere, and it correlates with regions of anomalous ice texture, meaning areas where the ice itself has been physically altered in ways consistent with disruption and thermal processing. The carbon dioxide is not randomly smeared across the surface. It follows the geology. Wherever the ice has been broken and refrozen, the carbon dioxide signal is stronger. Wherever the ice is old and undisturbed, the signal weakens or disappears. This correlation is what transforms the Webb result from a single localized detection into a surface-wide pattern. If carbon dioxide appeared in just one spot, you might argue for a local anomaly, a single event, a one-time disruption that happened to deliver ocean material to the surface. But when the same chemical signature appears across multiple independent chaos regions, all showing the same relationship between carbon dioxide abundance and ice disruption, the argument for a systematic process becomes much stronger. The ocean is not leaking in one place. It is leaking wherever the crust has been recently broken. The chemistry follows the geology with a consistency that is difficult to dismiss. The Yoffe team also found that the distribution of volatiles on Europa reflects not just where material is deposited, but where the surface is best able to retain it. Fresh, disrupted ice with anomalous texture appears to hold onto carbon dioxide more effectively than old, radiation-processed ice. This makes physical sense. Radiation destroys carbon dioxide over time. Fresh surfaces have had less exposure. The pattern of carbon dioxide abundance is therefore a combined signal. It tells you both where material arrived from below and how recently the surface was renewed. Every chaos region is a timestamp, marking a moment when the ice opened and the ocean spoke. Now consider what this means for the larger question of habitability. Before Webb, the case for Europa as a habitable world rested on indirect evidence. Magnetic field data implied a salty ocean. Tidal heating calculations showed the ocean could remain liquid. Surface geology suggested interior activity. Modelling predicted that water-rock interaction on the seafloor could produce chemical energy. All of these lines of reasoning were sound, but they were all inferences, conclusions drawn from data that did not directly reveal the ocean's chemical composition. The ocean could have been habitable. It also could have been a sterile, chemically inert body of water, salty but devoid of the reactive compounds that life requires. Webb changed the inferential distance. By detecting ocean-sourced carbon on the surface, it provided the first direct chemical evidence that the ocean contains one of the essential elements for biology in a form that reaches the exterior of the moon. This is not the same as proving the ocean is habitable. Carbon dioxide alone does not make an environment habitable, but it closes one of the most important gaps in the habitability argument. The ocean has carbon. The carbon is mobile. It moves through the ice, and it arrives at the surface in geologically meaningful concentrations. The energy side of the habitability equation is equally important and equally unsettling in its implications. The radiation environment does more than complicate the interpretation of surface chemistry. It actively manufactures new compounds. The charged particles slamming into Europa's ice do not just degrade ocean-derived material, they build an entirely separate chemical layer on top of it, one dominated by oxidants, molecules that could serve as fuel for biology if they ever reach the liquid water below. The surface carries sulfur-bearing compounds as well, delivered from Io's volcanic eruptions and processed by radiation into sulfur dioxide and sulfuric acid. The radiation chemistry is more intricate than a simple statement about breaking molecules can convey. When a high-energy charged particle strikes water ice, it deposits its energy along a track, creating a cascade of secondary reactions. Water molecules split into hydrogen atoms and hydroxyl radicals. Some of these fragments recombine into hydrogen peroxide, a stable oxidant that accumulates in the ice. Some produce molecular oxygen, which can remain trapped in the ice lattice or escape slowly into Europa's thin atmosphere. The process is called radiolysis, and it has been operating on Europa's surface for as long as Europa has orbited within Jupiter's radiation belts. The result is a surface that is not just cold and icy but chemically processed, coated in a thin veneer of oxidants produced by billions of years of continuous irradiation. The radiation does not treat the surface uniformly. Jupiter's magnetic field concentrates charged particles more heavily at certain latitudes and longitudes, creating a pattern of radiation exposure that varies across the Moon. The trailing hemisphere, the side facing backward along Europa's orbital path, receives a stronger particle flux than the leading hemisphere. This asymmetry shows up in the surface chemistry. The trailing hemisphere is richer in sulfur compounds and radiation products, while the leading hemisphere, where Tara Regio sits, is relatively less processed. This matters for the Webb detection because it means the carbon dioxide in Tara Regio has had comparatively less radiation exposure than it would on the opposite side of the Moon, potentially preserving more of the original chemical character of the ocean-derived material. Over time, radiation transforms the surface into a layered chemical record. Freshly deposited ice from below starts with whatever composition it carried from the ocean. Within decades to centuries, radiation begins altering the top few centimeters, creating oxidants and breaking down unstable molecules. Over thousands of years, the radiation-processed layer thickens. Over millions of years, virtually all of the original surface chemistry is overwritten by radiation products. The age of the surface determines how much of the original ocean signal survives. In chaos terrain, where the surface has been recently renewed, more of the original chemistry persists. In old, undisturbed plains, the radiation has had longer to erase the ocean's fingerprint. This is why Webb's detection in geologically young chaos terrain is so significant. It is precisely the kind of surface where ocean-derived molecules would still be detectable before radiation erases them. These radiation-produced oxidants are not just chemical curiosities, they represent potential food for life. On Earth, many microorganisms derive their energy not from sunlight, but from chemical reactions between oxidants and reductants. At deep-sea hydrothermal vents, bacteria harvest energy from the reaction between oxygen dissolved in seawater and hydrogen sulfide or molecular hydrogen rising from the vent. The oxygen comes ultimately from photosynthesis at the surface, transported into the deep ocean by circulation. But the fundamental chemistry is simple. An oxidant meets a reductant. The reaction releases energy. Life captures that energy and uses it to grow. Europa has the same basic setup, with one critical modification. There is no photosynthesis, but Jupiter's radiation performs an equivalent function by creating oxidants on the surface through purely physical processes. If those oxidants are transported downward through the ice into the ocean, they would encounter reduced compounds produced by water-rock interaction on the seafloor. The chemical gradient between surface oxidants and seafloor reductants would create energy, not from biology, not from sunlight, but from the combination of radiation chemistry above and geochemistry below. Life would not need to invent photosynthesis to survive on Europa. It would need only to position itself at the boundary where these two chemical worlds meet. The question is whether surface oxidants actually reach the ocean. This is where the fractures detected by Juno become critical, and where the physical mechanisms of downward transport deserve closer attention than they typically receive in summary accounts of Europa science. There are several ways surface material could move through the ice shell, The first is direct fracture penetration. If cracks in the ice extend deep enough, surface material could migrate downward along fracture walls through a combination of gravity, thermal gradients, and vapor transport. Juno's microwave radiometer detected scattering features extending to depths of hundreds of meters. That is far deeper than surface radiation penetrates, but still far shallower than the full thickness of the shell. Direct fracture. Transport alone probably cannot deliver material from the surface to the ocean through 29 kilometers of ice, but it can get material into the upper layers of the shell where other transport mechanisms take over. The second mechanism is ice convection. If the ice shell is thick enough, the temperature difference between its warm base and cold surface can drive slow convective overturn within the ice itself. Warm, buoyant ice from deep within the shell rises toward the surface. Cold, dense ice from near the surface sinks. This overturn does not happen quickly. It operates on timescales of millions of years, with ice creeping through the shell at rates measured in centimeters per year. But over Europa's multi-billion-year history, convective overturn could have cycled material from the surface downward toward the ocean many times. Surface oxidants carried into the upper shell by fractures could be drawn deeper by convection, eventually reaching the warm base of the ice where melting releases them into the liquid ocean below. The third mechanism is foundering. In certain models, dense surface material enriched in salts and radiation products becomes heavy enough to sink through the ice. This process, analogous to tectonic subduction on Earth but operating in ice rather than rock, could carry surface chemistry downward in concentrated packets. Some researchers have proposed that Europa's ridge terrain, the double ridges that crisscross the surface, may form through a foundering process, where surface ice is pushed downward along fractures while warm ice rises to fill the gap. If this model is correct, downward transport of surface material is built into the very geological processes that shape Europa's most common surface features. None of these mechanisms has been directly observed. They are models, supported by physics and by analogy with processes observed on Earth, but not yet confirmed by measurement at Europa. What is confirmed is that the ice shell is fractured, that it is thick enough to potentially support convection, and that the surface chemistry produced by radiation is different from the chemistry expected in the ocean below. The chemical gradient exists. The physical pathways are plausible. Whether the transport rate is fast enough to deliver biologically meaningful quantities of oxidants to the ocean within the ocean's lifetime remains a question that Europa Clipper's radar and compositional measurements may help. Answer. A 2026 study on Europa's habitability summarized the current state of the evidence by noting that Europa appears to have all three requirements for life. Liquid water exists in enormous quantities beneath the ice. Jupiter's radiation creates oxygen and other reactive chemicals that could fuel biological processes if they reach the ocean. And the essential chemical building blocks for life, including carbon now confirmed by Webb, are likely present. The study was careful to note that having the ingredients does not guarantee the recipe. Life requires not just the right elements and energy, but also the right conditions for complex chemistry to organize into self-replicating systems. Whether Europa's ocean provides those conditions remains unknown. This is the tension that the word disturbing captures. Not that Webb found proof of life, not that Europa is definitely inhabited, but that the evidence is accumulating in a direction that makes it increasingly difficult to dismiss Europa as merely interesting. Each new measurement closes another gap. First, the ocean was confirmed, then tidal heating was quantified, then salt from the ocean appeared on the surface, then carbon from the ocean appeared on the surface, then fractures in the ice were detected reaching hundreds of meters deep. Then the carbon dioxide was found to correlate with disrupted terrain across multiple regions. Each finding alone is incremental. Together they form a pattern that points toward a chemically active ocean world system, where the ingredients for habitability are not just theoretically plausible but observationally grounded. The discomfort comes from what this pattern demands of us. If Europa's ocean has liquid water, carbon, chemical energy, and a mechanism for cycling material between the surface and the deep, then either life exists there and we have not yet detected it, or the conditions for life are met and life did not arise, which would tell us something equally profound about how rare biology is in the universe. Both outcomes are consequential. Both reshape our understanding of what it means for a world to be habitable. and both become harder to avoid asking about as the chemical evidence sharpens. There is also a subtler disturbance embedded in the Webb data, one that has less to do with biology and more to do with perception. Europa has been a famous moon for a long time. It appears in mission plans, in astrobiology discussions, in science fiction. Most people who follow space science have heard of Europa's ocean. It has become familiar, even comfortable, a possibility that sits in the background of planetary science like wallpaper. Everyone knows Europa might be interesting. Few people feel the physical weight of what that means. Webb's contribution is not to add Europa to the list of interesting places. Europa was already on the list. Webb's contribution is to make the ocean feel real in a way that older data did not. When the evidence for the ocean rested on magnetic field measurements and thermal models, it was easy to hold Europa at arm's length. An interesting hypothesis, a candidate for further study. When the evidence includes chemical fingerprints of ocean material showing up on the surface in the exact places where the ice has been recently broken, the ocean stops feeling hypothetical. It starts feeling physical. It starts feeling close. Not close in distance. Europa is still roughly 628 million kilometers from Earth at its nearest approach, but close in the sense that a hidden environment is pressing against its own ceiling and leaving traces that a telescope can read from across the solar system. That is what disturbing means in the context of this story. It does not mean frightening. It does not mean that something sinister lurks beneath the ice. It means that better observation has made Europa's ocean world reality feel more concrete, more chemically detailed, and more difficult to file away as a distant theoretical possibility. The smooth white surface that looks so clean and inert in photographs is, according to the chemistry, a thin frozen membrane stretched over a liquid world that contains carbon, salt, energy, and geological processes capable of moving material between its interior and its exterior. We knew pieces of that before Webb. We did not know them with this degree of chemical specificity. And specificity in science is what separates a possibility from a constraint, and maybe from a measurement. The comparison with other ocean worlds in the solar system sharpens this point. Saturn's moon Enceladus is the only other body where direct sampling of subsurface ocean material has occurred through the Cassini spacecraft flying through plumes of water vapor erupting from the moon's south pole. What Cassini found in those plumes deserves more than a passing mention, because it sets the standard for what ocean world chemistry looks like when you can actually sample it. During its flybys between 2005 and 2017, Cassini flew through Enceladus's plumes repeatedly, each time capturing particles and gases with its onboard instruments. The results built a chemical portrait of the ocean below that no remote telescope could match. The plumes contained water vapor, which was expected, but also sodium chloride and sodium bicarbonate, salts that indicated the ocean had been in prolonged contact with rock. Cassini detected silica nanoparticles, tiny grains of silicon dioxide only 6 to 9 nanometers across. On Earth, silica nanoparticles of that size form only in hydrothermal systems, where water interacts with rock at temperatures above approximately 90 degrees Celsius. Their presence in the plumes implied active hydrothermal vents on Enceladus's seafloor, where hot water was dissolving rock and precipitating silica as it cooled and mixed with the colder ocean. Then came the detection of molecular hydrogen in the plume gas. Molecular hydrogen is produced on Earth through the same serpentinization process that operates on Europa's seafloor, the reaction between seawater and iron-rich minerals that releases hydrogen as a byproduct. On Earth, that hydrogen is one of the primary chemical fuels that sustain microbial communities at hydrothermal vents. Methane-producing archaea, among the most ancient lineages of life on Earth, use molecular hydrogen combined with carbon dioxide to generate energy. Finding molecular hydrogen in Enceladus's plumes meant that the same chemical fuel source that powers deep-sea life on Earth is available in a confirmed ocean world elsewhere in the solar system. Cassini also detected simple organic molecules in the plume material, including formaldehyde and acetylene, as well as more complex organics with molecular masses suggesting compounds containing nitrogen and oxygen, in addition to carbon and hydrogen. These organics were not proof of biology. They could form through abiotic chemistry at hydrothermal vents, but their presence confirmed that Enceladus's ocean is not a simple salt solution. It is a chemically complex environment where organic synthesis is occurring, whether biologically or geochemically. Enceladus is a powerful case for habitability. But Enceladus is tiny, roughly 500 kilometers in diameter, with a much smaller ocean and less tidal energy than Europa. Europa's ocean is vastly larger, likely older, and potentially more chemically complex due to the greater scale of water-rock interaction on its seafloor. Where Enceladus gives us a direct taste of ocean world chemistry through plume sampling, Europa gives us something different but complementary. A spatially resolved chemical map of where ocean material reaches the surface, laid out across a geologically complex terrain that spans an entire hemisphere. Webb cannot fly through a plume. It cannot directly sample Europa's ocean material the way Cassini sampled Enceladus. But what Webb can do, and what it has now done, is read the surface chemistry with enough precision to detect ocean-derived compounds in geologically meaningful contexts. The result is a different kind of evidence, indirect but spatially resolved, chemically specific, and tied to geological features that have independent explanations rooted in ocean surface exchange. Enceladus gave us a taste of what ocean worlds contain through direct sampling. Europa is giving us a chemical map of where its ocean reaches the surface, drawn in carbon dioxide and salt on a canvas of fractured ice. Together, these two moons are building the case that ocean worlds in the outer solar system are not exotic exceptions. They are chemically active environments where the ingredients for habitability are present and measurable, even from enormous distances. The map is still incomplete. Webb observed only portions of Europa's surface. Not all chaos regions have been examined at the same spectral resolution. The chemical inventory is limited to compounds that have strong spectral features in the near-infrared, meaning that other potentially important molecules may be present but undetectable with Webb's instruments. And this limitation is worth dwelling on, because the molecules that matter most for the question of life are precisely the ones Webb is least likely to see. Carbon dioxide is the simplest carbon-bearing molecule that could survive on Europa's surface long enough to be detected from deep space. It is stable enough to persist in young chaos terrain for geologically meaningful periods before radiation destroys it, and it has strong, well-characterized absorption features in the near-infrared that Webb's spectrograph can resolve cleanly. But carbon dioxide is a long way from the molecular complexity that biology requires. Life on Earth uses amino acids, lipids, nucleotides, sugars, molecules built from dozens or hundreds of atoms arranged in specific three-dimensional architectures. The question that naturally follows Webb's detection is whether any of these more complex organic molecules exist on Europa's surface. The honest answer is that Webb probably cannot tell us, and the reason is not a limitation of the telescope. It is a limitation imposed by Europa's environment. Complex organic molecules are far more fragile than carbon dioxide. They contain bonds that break easily under radiation, particularly the carbon-hydrogen and carbon-nitrogen bonds that are central to biological chemistry. On Europa's surface, where Jupiter's radiation continuously bombards the ice, a complex organic molecule deposited from below would begin degrading almost immediately. Within years to decades, radiation would fragment it into simpler compounds, eventually converting it to carbon dioxide, carbon monoxide, and other small molecules that represent the thermodynamic end state of radiation processing. The more complex the original molecule, the faster it breaks down. Amino acids might survive for centuries in fresh chaos terrain. Larger structures like peptide chains or lipid membranes might last only years. By the time Webb observes the surface, the radiation has already done its work, reducing whatever complexity the ocean delivered into the simplest molecular forms. This means that the absence of complex organics in the Webb data does not weaken the habitability case. It reflects the physics of Europa's radiation environment, not the chemistry of the ocean below. The ocean could be producing complex carbon compounds, delivering them to the surface through chaos terrain, and radiation could be destroying them faster than they accumulate. Webb would see only the debris, the carbon dioxide, and simple fragments that survive long enough to be detectable. The original molecules would be gone, their complexity erased by the same radiation that makes the surface such a hostile place for chemical preservation. This is why close-range observation matters so much. Europa Clipper's mass spectrometer and dust analyzer will not be limited to infrared spectroscopy from hundreds of millions of kilometers away. They will capture particles directly from the space around Europa, particles sputtered off the surface by radiation impacts or ejected by any transient plume activity. These particles will have been exposed to radiation for much shorter periods than the surface ice web observed. Some may contain molecular fragments that preserve information about the original compounds that were delivered from the ocean. If Europa Clipper detects complex organic molecules or even fragments that imply complex precursors, it would represent a qualitative leap beyond what Webb can achieve. Webb found carbon. Europa Clipper might find what that carbon was part of before the radiation took it apart. That contact is coming, and the chemical map Webb is building right now will determine exactly where the next generation of spacecraft points its instruments when it arrives. What those missions are, what they carry, and what it means that we're about to get our closest look at an alien ocean's surface expression is where this story reaches its final act. On October 14th, 2024, a SpaceX Falcon Heavy rocket lifted off from Kennedy Space Center in Florida, carrying the largest spacecraft NASA has ever built for a planetary mission. Europa Clipper, a solar-powered orbiter spanning more than 30 meters with its arrays deployed, roughly the length of a basketball court, began a journey of approximately 2.9 billion kilometers toward Jupiter. The spacecraft performed a gravity assist flyby of Mars on March 1st, 2025, and will swing past Earth in December 2026 before entering orbit around Jupiter in April 2030. Once there, it will not orbit Europa directly. Jupiter's radiation belts are too intense for a spacecraft to survive prolonged exposure at Europa's orbital distance. Instead, Europa Clipper will orbit Jupiter on a wide, looping trajectory that carries it in and out of the radiation zone, performing 49 close flybys of Europa over the course of its primary mission. Some of those flybys will bring the spacecraft within 25 kilometers of the surface, close enough to read the ice in ways no telescope, no matter how powerful, can match from a distance of hundreds of millions of kilometers. Europa Clipper carries 9 scientific instruments designed to investigate whether Europa's ocean could support life. Among them is an ice-penetrating radar called the Radar for Europa Assessment and Sounding, Ocean to Near Surface, which will send radio waves through the ice shell and listen for reflections from subsurface boundaries. If liquid water pockets or the ocean-ice interface lie within radar range, this instrument could detect them directly, providing the first measurement of ice shell structure beneath the surface rather than inferred from orbit. The spacecraft also carries a thermal imager that will map surface temperatures at high resolution, identifying warm spots that could indicate recent geological activity or thin ice. A mapping spectrometer will examine the surface composition at scales far finer than Webb can achieve, identifying minerals, salts, organics, and ices across Europa's entire surface. A mass spectrometer will analyze any material the spacecraft flies through, including particles sputtered off the surface by Jupiter's radiation or, if plumes are active during a flyby, water vapor and ice grains ejected from the interior. A dust analyzer will capture and examine microscopic particles from the space around Europa, potentially sampling ocean-derived material that has escaped through the ice. Every one of these instruments was designed with a specific question in mind. What is the ice shell made of, and how thick is it? What compounds exist on the surface, and where did they come from? Is there thermal or geological activity happening now? Is there material from the ocean accessible near the surface, or in the space around the moon? And behind all of these technical questions sits the larger one, the one that has driven Europa science for decades. Could this ocean support life? Webb's observations are already shaping how Europa Clipper will answer those questions. The chemical map that Webb assembled, showing where carbon dioxide concentrates, where chaos terrain correlates with volatile enrichment, and where the ice texture suggests recent disruption, gives the mission team a guide. It tells them where to look first. When Europa Clipper swoops past Tara Regio, it will do so knowing that Webb detected ocean-sourced carbon there. The radar will probe the ice structure beneath that specific region. The spectrometer will examine the surface chemistry at resolutions hundreds of times finer than Webb could achieve. The thermal imager will search for temperature anomalies that might indicate ongoing exchange between the surface and the ocean below. This is not a general survey. It is a targeted investigation informed by chemical evidence that did not exist before 2023. Webb told Europa Clipper where the ocean's fingerprints are strongest. Europa Clipper will go there and read them up close. Europa Clipper is not alone in the outer solar system. The European Space Agency's JUICE mission, which stands for Jupiter Icy Moons Explorer, launched in April 2023 and is currently en route to the Jupiter system, expected to arrive in July 2031. JUICE will study Jupiter and 3 of its large moons, Ganymede, Callisto, and Europa, though its primary focus is Ganymede, where it will eventually enter orbit. JUICE will perform 2 close flybys of Europa, fewer than Europa Clipper's 49, but its instruments will provide complementary data from different orbital geometries and at different times. Between these 2 missions, scientists will have the most comprehensive dataset ever assembled for any ocean world beyond Earth. The convergence of these missions with Webb's chemical findings creates a scientific moment unlike anything in the history of planetary exploration. For the first time, we are approaching an ocean world not with general curiosity, but with specific chemical questions derived from remote observation. We know carbon dioxide concentrates in chaos terrain. We know the ice is fractured to significant depths. We know salt from the ocean has been found on the surface. We know the surface chemistry correlates with geological features that indicate recent disruption. Every one of these findings becomes a target, a waypoint, a place where close-range instruments can test what remote observation suggested. But here is what makes this moment genuinely new and genuinely unsettling if you sit with it long enough. Everything we have discussed in this story, the carbon dioxide, the salt, the chaos terrain, the fractures, the isotope ratios, the radiation chemistry, all of it was gathered by instruments that never touched Europa. Webb is 1.5 million kilometers from Earth, pointed at a moon more than 600 million kilometers away. The Galileo spacecraft flew past Europa at distances of hundreds of kilometers. Hubble observed from Earth orbit. Juno measured microwaves during a single flyby. We have assembled a detailed chemical and geological portrait of an alien ocean world without ever making physical contact with its surface. We have never touched the ice. We have never tasted the water. We have never lowered anything through the crust. And yet we can tell you where the ocean's carbon shows up on the surface, what form it takes, how recently it was deposited, and which geological processes likely delivered it. That capability is extraordinary, and it should be recognized as such before we rush forward to the next discovery. Humanity built a telescope, placed it at a gravitational balance point in deep space, pointed it at a moon of Jupiter for a few minutes, and extracted chemical information about a buried ocean from the infrared light reflected off the ice. The distance between the telescope and the target is so vast that light takes more than half an hour to cross it. The molecules being detected are measured not by touching them, but by the specific wavelengths of light they absorb when infrared radiation passes through them. The entire analysis depends on understanding physics at a level precise enough to distinguish one molecular signature from another across interplanetary distances. This is not science fiction. This is what happened in September 2023, and it is still happening as new observations are analysed and published. What does it mean, then, that we can read an alien ocean's chemistry through its ice from across the solar system? It means the era of treating ocean worlds as abstract possibilities is ending. Europa is not a thought experiment. It is not a hypothesis waiting for a future mission to become real. It is a measurable, mappable, chemically legible system whose buried ocean is expressing itself through the surface in ways our instruments can detect right now. The missions heading there will sharpen the picture. They will fill in gaps that remote observation cannot reach. They will answer questions Webb cannot, but the fundamental shift has already occurred. We are no longer speculating about whether Europa's ocean connects to its surface. We are mapping where the connections are strongest and what chemistry they carry. This shift carries a weight that is easy to underestimate. For most of human history, the ocean worlds of the outer solar system were points of light. Jupiter's moons were faint dots that required a telescope to see at all. Even after the Voyager flybys revealed Europa's cracked ice surface, the moon remained distant and abstract, a place scientists talked about in conditional tenses. It could have an ocean. It might be habitable. It may contain the ingredients for life. Each conditional was a buffer, a way of acknowledging the scientific interest while maintaining a comfortable distance from the implications. Webb's data erodes those buffers. When the evidence was purely geophysical, magnetic fields and gravity measurements and thermal models, the ocean felt theoretical. You could file it alongside other scientific inferences, important but not visceral. When the evidence becomes chemical, when you can point to a specific molecule on a specific patch of ice and say that molecule came from the water below, the ocean stops being theoretical. It becomes a source, a producer of observable chemistry, a system that leaves marks on its own ceiling. The abstraction collapses into something more immediate, and the conditional language starts to feel inadequate. This is the real meaning of the word disturbing in this story. Not that something dangerous was found, not that life was confirmed, not that Webb captured an image of something crawling beneath the ice. The disturbance is epistemic. It is the disturbance of having a familiar idea suddenly become unfamiliar because the evidence supporting it got too specific to ignore. Most people who have heard of Europa's ocean treat it as interesting background knowledge, a fun fact about the solar system. Webb's data makes it harder to leave it in the background. An ocean with carbon. An ocean with salt. An ocean whose material is reaching the surface through cracks in geologically young ice. An ocean that may have existed for 4 billion years, heated by tidal forces pressing against a fractured shell in permanent darkness, beneath a radiation-blasted surface that carries the chemical record of what lies below. That is not a fun fact. That is a physical system of staggering consequence, and we are only now developing the tools to read it properly. There is a deeper challenge here, one that extends beyond Europa and into how humanity relates to the universe it is beginning to explore. We have spent centuries looking outward. We mapped the planets. We catalogued the stars. We measured the expansion of the cosmos. But for most of that history, looking outward meant looking at surfaces, at light curves, at gravitational signals. We saw the exteriors of things. What Webb represents, in this specific case, is the beginning of looking beneath. Not beneath the ice in a literal sense. We have not drilled through anything, but beneath the surface layer of data into the chemical interior of another world. We are reading what is inside Europa by analysing what leaks out. We are diagnosing an ocean the way a physician diagnoses an internal condition by reading external symptoms. The surface chemistry is the symptom. The ocean is the patient. And the diagnosis is that the patient is more active, more complex, and more chemically connected to its own exterior than the smooth white surface ever suggested. This transition, from seeing surfaces to reading systems, is what makes Europa feel different under Webb's gaze. Older images of Europa show a beautiful pale sphere, clean lines of fractures against white ice, elegant and distant. Webb's data does not replace those images. It annotates them. It says that the white surface you are looking at is not inert. The fractures are not just cracks. The discoloured patches of chaos terrain are not just rough spots. They are chemical delivery zones where a hidden ocean is depositing material that carries information about its composition. The beauty of the old images remains, but the meaning changes. Europa is no longer a portrait. It is a document, and we are learning to read the language. Consider what it will feel like when Europa Clipper returns its first close-range data from Tara Regio. The spacecraft's mapping spectrometer will examine the surface at resolutions measured in meters rather than the hundreds of kilometers that Webb achieves from deep space. The ice-penetrating radar will probe the subsurface structure, potentially revealing the boundary between ice and liquid water. The thermal imager will search for heat anomalies that indicate where the interior is warmest. If the mass spectrometer detects particles from the ocean in the space around Europa during a flyby, scientists will have direct samples of subsurface material for the first time. Each of these measurements will refine the picture Webb sketched. Where Webb saw carbon dioxide concentrated in chaos terrain, Europa Clipper may see the detailed mineral assemblages that reveal exactly how that carbon was transported through the ice. Where Webb measured an ambiguous carbon isotope ratio, Europa Clipper's closer instruments may narrow the uncertainty enough to distinguish between biological and non-biological formation pathways. Where Webb detected no plumes during a single observation window, Europa Clipper's 49 flybys over several years will provide dozens of opportunities to catch transient activity if it occurs. The 2026 YOFO study, which showed carbon dioxide extending across multiple chaos terrains and correlating with anomalous ice texture, gives Europa Clipper an even richer target map than the original 2023 papers provided. Each chaos region identified as a site of volatile enrichment becomes a priority target for close observation. The spacecraft will not arrive at Jupiter blind. It will arrive with a chemical atlas assembled by the most powerful space telescope ever built, and it will use that atlas to guide the most detailed investigation of an ocean world ever attempted. But even if Europa Clipper confirms every inference Webb made, even if it finds organic molecules on the surface, thermal anomalies over chaos terrain, subsurface liquid water within radar range, and plume material during a flyby, the deepest question will remain unanswered. Is anything alive down there? That question cannot be answered by an orbiter. It probably cannot be answered by any mission currently planned. Answering it would likely require landing on the surface, drilling into the ice or sampling plume material directly, and analyzing it with instruments designed to detect biosignatures at the molecular level. Such a mission exists in concept but not yet in hardware. It would be one of the most technically challenging endeavors in the history of space exploration, requiring a spacecraft that can survive Jupiter's radiation long enough to operate on the surface, drill through ice of unknown hardness and structure, and perform biochemical analysis in one of the harshest environments in the solar system. That mission may come. If Europa Clipper's data strengthens the habitability case, the scientific and political will to send a lander could build. But even without a lander, even without a definitive answer to the life question, the evidence already in hand changes how we relate to Europa. We can no longer treat it as a distant candidate. It is a world with a measurable chemical connection between its surface and its ocean. It is a world where carbon from below arrives at the ice in the places where the crust has been recently broken. It is a world where the conditions for habitability are not speculative but observationally constrained. And here is the thought that this story leaves you with. Europa has been there for 4.5 billion years. Its ocean has been liquid for most of that time. The tidal engine that heats its interior has been running since the Laplace resonance locked Io, Europa, and Ganymede into their orbital dance billions of years ago. Whatever is happening beneath that ice, whether it is complex chemistry or simple geology or something we do not yet have a category for, has been happening in darkness and silence for longer than life has existed on Earth. We are not discovering Europa. We are catching up to it. The ocean was there before we had telescopes. The carbon was cycling before we had spectrographs. The chaos terrain was forming and refreezing before any human eye looked up at Jupiter and wondered what those tiny points of light might be. What Webb did was not reveal a secret. It was to make visible something that was already happening, something that has been happening for eons, in a place where no one was watching. The ice cracked, the ocean pushed material upward, the carbon settled into the refrozen surface. Jupiter's radiation broke some of it down. More material arrived from below. The cycle continued. And then, in 2022, a telescope that had been in space for less than a year pointed its infrared spectrograph at that surface for a few minutes and read the chemical record that billions of years of ocean surface exchange had written in the ice. The real disturbance is not what Webb found. The real disturbance is that Europa was doing this the entire time, and we only just became capable of noticing. A hidden ocean, twice the volume of all the water on Earth, pressing against a cracked shell of ice, depositing its chemistry on the surface in patterns that correlate with geological disruption, carrying carbon from its depths to its ceiling, operating in total darkness at the bottom of a gravity well around the largest planet in our solar system. And the more precisely we observe it, the less it looks like a distant possibility, and the more it looks like a world, a real, physical, chemically active world buried under ice, waiting beneath a surface that was never as quiet as it appeared. We pointed our best telescope at Europa. We read the ice. And what the ice said was that the ocean beneath it is not a hypothesis. It is a system, with chemistry, with energy, with carbon, with geological processes that connect the deep to the surface and the surface to the deep. We cannot go there yet. We cannot touch the water or test it or know for certain what it contains beyond what leaks through the crust. But we can no longer pretend we do not know it is there, or that what it contains does not matter. Europa is not creepy. It is not mysterious in the way that word is used to avoid being specific. It is chemically serious. It is oceanographically real. And under better observation, it becomes not less strange but more consequential, more physical, more difficult to set aside. That is what it means to see something for the first time, not to discover that it exists, but to see it clearly enough that you can no longer look away.